We present an approach for reconstructing the 3D shape of articulated object categories, such as animals, for which limited annotations are available. In this setting, the annotation scarcity makes learning a 3D reconstruction model particularly challenging. However, the web is a great source of unlabeled images for any object. We propose an approach to effectively utilize supervision from unlabeled web images and improve the performance of existing 3D reconstruction methods. The whole process requires only a few images labeled with 2D key points. Let's look at our proposed approach in more details. We start by training a 2D pose estimation network H with a small number of images labeled with 2D key points. This kind of annotation is easy and fast to acquire for any object category. Then, we use a pose estimation network to generate key point pseudo-labels on unlabeled images from the web. A key insight is that current 2D key point estimators are accurate enough to create robust 2D key point detections on unlabeled data, even when trained with a limited number of images. Another insight is that the unlabeled images from the web increase the variability of several important factors for 3D reconstruction, such as the camera viewpoints, articulations, and image backgrounds. These factors are important in order to create generalizable 3D reconstruction models. However, the automatically acquired images contain a high proportion of low-quality images with wrong or heavy truncated objects. Thus, to effectively use images from the web, we employ a data selection criterion to automatically create a curated subset that includes web images with high-quality pseudo-labels. We investigate several selection criteria for this step. These contain a criterion based on the estimated confidence from the key point pseudo-labels, as well as some consistency-based criteria. Our final step is to train our model with images from the small initial label set, as well as with the selected images and pseudo-labels from the previous step. We offer two examples for data selection criteria. Cross-model consistency uses the discrepancy between the estimated key points from two 2D key point estimation networks with different architectures as a proxy for the quality of the generated pseudo-labels. Our insight here is that the two models can have different structural biases and can learn different representations from the same image. Going one step further, we use the consistency between the estimated key points from a 2D key point estimation network and the projected key points from the shape predictor F. Our insight here is that the two models employ different paradigms for estimating 2D key points and can have distinct failure modes. 2D key point detectors use a bottom-up approach to determine the locations of 2D key points, while their predictions are more pixel accurate than the reprojected key points from a 3D mesh. They are not constrained in any way and mainly rely on local cues. On the other hand, 3D shape predictors estimate key points as part of a 3D mesh, which constrains the predictions with a specific mesh topology. This makes the predictions more robust. Now, let's have a look at some results. In this paper, we show quantitative and qualitative results on multiple datasets like Pascal VOC, Animal Pose, MS Coco, and CUB. I won't go through all the experiments and results in this video, but if you're interested, do check the paper. Let's have a look at some results from Pascal. The 3D shape prediction method used here is ACSM. We train ACSM with 150 images labeled with 2D key points, establishing a stronger baseline, which we dub ACSM hours. We observe that naively using all web images and generated key point pseudo-labels leads integrated performance. Finally, we see that with a data selection method, we can effectively utilize web images and improve the performance of the fully supervised baseline. Among the data selection criteria used, the consistency-based ones achieve the best results. We also saw some results on animal pose. We can see that the results are consistent with the ones seen previously for the Pascal dataset. Here, we saw some results for starting the whole process with different number of images labeled with 2D key points. We notice that our approach is effective even when only 50 labeled images are used. More importantly, we see that models trained with just 50 labeled images and Keypoint Pseudo-labels outperform the fully supervised models trained with more annotation. Next, we show some results with a different 3D reconstruction method, CMR. The results are on CUP touch. We also visualize some reconstructed shapes for models trained with and without Keypoint Pseudo-labels. Visualize the prediction from models trained without a data selection criterion and with selected images from the web. Finally, we show some results from all baselines and data selection approaches. Thank you very much for your attention. If you are interested, check out our code and website.